Okay, I think that it does now. And we are officially live. So welcome everyone to a special RBSP seminar dedicated to Elfin mission from UCLA. We have two fantastic speakers today that are going to overview different aspects of the mission for us. Xiaojia Zhang is joining us from University of Texas at Dallas. Dr. Zhang received her PhD in space physics in 2014 from UCLA, where she's been working on the excitation of emic wave harmonics in Earth magnetosphere. Then she worked for a couple of years there on mainly focusing on wave particle interaction data analysis from various magnetospheric missions, both at Earth and such as Van Allen probes, and Jupiter, such as Juno, and most recently on the first UCLA CubeSat mission, Elfin. And in August 2022, so relatively recently, she joined the Department of Physics at UT Tech Dallas as associate professor. And today she will be talking about new findings from the Elfin mission, and she will be focusing on the inner magnetosphere. Anton Artemyev is joining us from UCLA. Anton received his PhD in 2010 from Space Research Institute of Moscow in theoretical physics, where he was studying the structure of magnetotail current sheet and structure and dynamics of magnetotail current sheet. Then, after graduation, he joined LPSC2E CNRS lab in Orléans in France as a postdoc, and there his main topic was wave particle interactions in radiation belts. In 2015, Anton joined UCLA as a researcher to work on Themis, Artemis, and Elfin measurements. And today, Anton will be talking to us about Elfin findings in the Magnetotail. And quick note to all, we will be holding back all the questions until the both speakers have a chance to present their talk, but of course the chat is always open for putting in early questions and in discussion. Now, without further ado, Xiaojia, please take it away.
Yeah, thank you for the introduction. Can you see my screen okay?
Yes.
Okay, yeah. So as Sasha talked about, I'm Xiaojia Zhang from UT Dallas, and today I will be talking about or summarizing Elfin results in the inner magnetosphere on behalf of the entire Elfin team. By no means that this will include all the results in the inner magnetosphere, but rather I will just highlight several representative studies in this topic. So let's first get into what is Elfin. So Elfin actually are two identical 3U CubeSats orbiting the Earth at a low altitude orbit, about 420 kilometer altitude in a polar and near circular orbit, with the primary objective to address the relativistic electron precipitation mechanism. Each of the two Elfin probes, Elfin A and Elfin B, are actually equipped by two energetic particle detectors, one for electrons and one for ions, and also a flex gain magnetometer to detect those simultaneous emic waves reaching this altitude. So one thing to emphasize here is that the unique property of Elfin is that it spins. So that it spins in a way that the spin plane encompasses the background magnetic field, and so that in this way, the over half a spin Elfin was able to capture a full pitch angle spectra from 0 to 180-degree pitch angle for all the particle precipitation data, and also that it covers a relatively good energy range from 50 keV to about 5 MeV for both ions and electrons. So that's one thing being different from majority of the CubeSats in this altitude. And another thing to emphasize that is Elfin is a purely student-built and lead mission at UCLA campus. By students, we mainly talk about undergrad students here. And since its launch in 2018, most of the probes have worked well until 2022. So during this 4-year interval in orbit, Elfin was able to capture more than 10,000 radiation belt crossings with all the plots available online, publicly available online, and also the data being released through the speeders, so that everyone is welcome to use this data from our community. And we talk about this Elfin being in this LEO orbit with relatively short orbital period. So during its 3-year routine operation, Elfin was able to capture or cover a relatively good MOT region. Sorry, it was actually able to cover all the MOT region for the electron data, but only available for this NICEID season, for the last NICEID season. For the ion data, as you can see from this data set coverage in the MOT and magnetic latitude domain. And again, that due to its orbit at low altitude, Elfin has been able to obtain, or we have been able to obtain relatively fruitful conjunctions with multiple NASA missions or NOAA missions, so that we have there's often available information of both the waves from these other missions and also the precipitation data obtained from Elfin during this kind of conjunction events. About this, we will show a few examples in the following slides for each of the topics that we will be covering in this presentation. So one thing to remind you before we go into details is that Elfin, as we talk about, can capture those electrons coming from different pitch angles, and more often that we show this data in the as shown in the left panels here, that we separately plot this perpendicular electron energy spectra as those electrons outside the local loss cone, and those precipitating or parallel electrons as electrons that fall into this local or bounce loss cone along the trajectory. And we often use this ratio between the precipitating and perpendicular populations as a way to show the precipitation intensity devoid of the spatial variation of the trapped electron fluxes along the orbit. So these are actually will be the format we will be showing the Elfin data in this presentation, just to prepare you for the later slide. So after all this introduction of Elfin mission and Elfin data set, so let's get into details of what we can learn from this unique data set that has this kind of pitch angle resolution for the precipitation data. So a little bit more about the background, that we all know that there are various of plasma waves excited in our magnetosphere. So as a result, that we can, or we expect to have various precipitation patterns, as we can see from the magnetosphere. So as a result, actually, Elfin was able to capture all sorts of, or almost all precipitation patterns due to various scattering mechanisms across different regions, as we marked here. here are just a snap view of what the Elfin data look like here for each of these precipitation pattern. As you can see that they are actually driven by different scattering mechanisms as marked on the top for each panel that operate on electrons, often at different energies or at different regions. As promised, in this presentation, we will be focusing on those precipitation pattern as seen in the inner magnetosphere, and Anton will cover those precipitation that we see in the Magnetotail region in the lower panels here. So let's get into more details of what we can learn from this Elfin data set for each of these precipitation pattern that we'll be covering in this presentation. The first one we will be talking about is the Whistler mode coarse waves or Whistler mode waves in general in this night to downside sector. So the first thing we can see from this Elfin data set is exemplified by these two orbits from Elfin in the radiation belt region, as you can see here by these two rectangular regions. That is, there are two possible types of precipitation that can be driven by this more or less field-aligned or quasi-field-aligned Whistler waves, corresponding separately to this energy spectra in the right panel here. So the first energy spectra corresponding to the first event, and second corresponding to the second event on the left. So as we can see from this energy spectra, which shows on the y-axis this precipitation intensity signified by the precipitating to perpendicular flux ratio as a function of energy. So we can see that during the first spectra, actually this flux ratio decreases with energy as expected for those field-aligned Whistler wave scattering. And but on the contrary, or being different, the second spectra here actually show quite intense precipitation with this ratio reaching 1 even at lower energies, and reaching above 1 actually at even higher energies. Based on this subspin resolution data, so that we actually see this rather this short time scale precipitation, or the so-called microburst precipitation as seen by Elfin in its routine and 1.5 second data. In other words, that this is due to time aliasing of the measurements, so that the precipitating and perpendicular fluxes are measured at different times, so that you end up with having this precipitation ratio or flux ratio being above 1 during this kind of short time scale precipitation events. And for completed statistics of typical energy spectra of driven by Whistler mode waves on the down to night side region, that please refer to more details from Tsai et al.'s paper in 2023 and 2024. So that we talk about being the first spectra being more or less the typical precipitation spectra driven by these field-lined Whistler waves. But one of these special cases for this microburst precipitation, actually that we also look at, or previous studies also look at the details about this microburst precipitation observed by Elfin. What's shown here on the left is another example of this microburst precipitation observed by Elfin during its traversal in the outer radiation belt region, as you can see from this L-shell domain. And these two bursts actually marked those microburst precipitation, as we can verify from this subspin resolution data. And during this event, we can see that the energy of this microburst precipitation actually reaches to relativistic energies about 700 or 800 keV, as we can see here. And during this event, then we are fortunate enough to still have this Western mode wave measurements from the conjugate equatorial spacecraft by RBSP. So from this panel, we can see RBSP captured this rather intense field-aligned Western mode coarse waves during this case, and which can potentially explain this microburst precipitation. And further test particle simulations showed that only those Western waves that are under ducted propagation to reach mid-latitude can explain this observed microburst precipitation expanding over such a wide energy range from tens of keV to about 1 MeV actually in this case. So this just indicates that this is possible or is likely that the ducted coarse waves play an important role for driving these relativistic electron microbursts. And of course that we can also conduct statistics of this microburst precipitation using not this 1.5 second data, by using this the so-called subspin resolution data that more details can be found in our 2022 paper about the microburst statistics. So that's more about, that's the two highlights that we wanted to cover here for this field-aligned coarse waves. And then another population or another type of precipitation are driven or can be driven by those still the same wave mode, Western mode coarse waves, but rather on the day side. So what's special about this, or what's different about this day side Western mode waves compared to the more commonly observed downside or night side course, is that these waves can approach oblique wave normal angles. And shown here are two example observations from Elfin in the radiation belt region again on the day side. So during the first event that we see this kind of loss cone overfilling with the precipitating to perpendicular flux ratio reaching above 1 at lower energies. And this study and also following studies have been attributing this loss cone overfilling by the nonlinear Landau resonance caused by this oblique Western waves that also observed in the conjugate equatorial region. And in the second event on the right, that we see this kind of quite intense precipitation, again, during these two interval that are conjugate to the oblique coarse waves observed by SAMAS during this event. That also through simulation demonstrated that this precipitation can be explained by higher order resonances with these oblique coarse waves. So overall, that these two lines of work or these two types of resonances actually provide a quite efficient mechanism for this relativistic or more energetic electron precipitation on the day side that we kind of are missing from our current radiation belt models. So that's why I just wanted to highlight this study here. And the next precipitation pattern I wanted to cover is the so-called quasi-periodic precipitation driven by those modulated Western waves in the flank regions, either on the downside or on the dusk side. So shown here, actually, before I start, this quasi-periodic precipitation is actually very commonly observed in Elfin dataset. So shown here is just one such example. As you can see, this periodic precipitation observed on the night side actually during this case. So in this event, we can see that the precipitation actually, as you can see from this panel, extends from 50 keV to about 400 keV in this event. So this energy range and also the distribution of this precipitation, precipitating flux ratio actually dictates the source being this modulated coarse waves in the equatorial region. But the connection between these two, between the modulated coarse waves and this quasi-periodic precipitation has not been directly established prior. So that's why in this study, by looking at also the conjugate measurements from summons, that the authors demonstrated that indeed during this event, that we have this modulated coarse waves modulated by the compressional ULF waves as marked by these black solid lines here. And by further comparing the spatial scale of this periodic precipitation at Elfin and this the wavelength of ULF waves observed by multiple summit spacecraft, that these two are being similar with each other, the authors concluded that the ULF wave modulated coarse waves are likely driving this quasi-periodic precipitation as we see at Elfin in the flank region or in this night side region during this event. And one thing to emphasize here is that during this kind of quasi-periodic precipitation event, that we can see it actually expands or occupies a quite large spatial domain or L-shell range from 6 to 9 in this event. So just indicating that this mechanism of driving the electron precipitation can affect our radiation biodynamics over a relatively wide L-shell range and also MLT domain. Yeah, so the next precipitation pattern I want to cover here is the so-called wisp precipitation in the Earth's inner radiation belt. So one thing to emphasize here is that the wisp precipitation has been observed by previous low altitude spacecraft. But what's new here again is that the Elfin was able to provide those precipitation or pitch angle distribution for this wisp precipitation in the inner magnetosphere, inner radiation belt. So that having this pitch angle distribution, one can estimate the wave amplitude of the source region, the wave amplitude of the source of this precipitation, so that to infer the wave intensity, right, from the VLF transmitters that drives this wisp precipitation. So that's one thing being new from the Elfin dataset in this regard. And we all know that this dispersion, of course, is caused by the variation of the FCE due to L-shell as it traverses, as basically the Elfin moves along the orbit. And another thing we can do is that we can look at this distribution of wisp events in those drift loss cone or in the bounce loss cone in a way that these local precipitation events can be further analyzed relative to the locations of these VLF transmitter stations as marked in the lower panels here. But I will not cover details here for the sake of time, but please feel free to refer to this Yang Shen's work in 2022 for more details on this regard. So the next topic I want to cover is those more higher energy precipitation or relativistic electron precipitation driven by EMIC waves. That on the left-hand side, we have 3 examples of EMIC-driven precipitation during these 3 consecutive Elfin orbits, actually demonstrating the consistent or persistent precipitation that lasts for more than 3 hours in UT, actually. Based on similar events like this kind of relativistic electron precipitation, we can obtain this statistical energy spectra driven by EMIC waves, as shown on the right-hand side plot. The red curve or red trace here shows the average precipitating to perpendicular flux ratio for this kind of events, where we can see that the flux ratio actually peaks or more or less saturates above about 1 MeV to about several couple MeV as expected by the for the imaging wave scattering. But in addition, we do see that this kind of low energy precipitation that accompany this relativistic electron precipitation during this kind of events. And as shown by previous works, that this low energy precipitation tail can be explained either by the resonance scattering of high frequency portion of imaging wave spectra, or by the non-resonant scattering of imaging waves with shortwave packets. Again, that please refer to the these two works for more details of their simulation work on this perspective. So lastly, that I just wanted to cover that with all the information that we obtained for the waves and obtained for the precipitation data at different LEO satellites, that we are at a point that we can verify whether or how well our quasi-linear wave diffusion model works compared to this Elfin dataset. So that's the last part I want to cover in this presentation. So by estimating the decay rate of the trapped electron fluxes or perpendicular electron fluxes during this prolonged intervals of moderately disturbed periods is exemplified by this left-hand side plot. The Marinas et al. Conducted actually a series of validation work to compare this directly estimated electron lifetime inferred from Elfin data with those electron lifetimes inferred from statistical wave models and our theory of wave-particle interaction, or the so-called quasi-linear diffusion model. So the right-hand side plot directly compared these two results in terms of electron lifetime. So the color-coded are the electron lifetime estimated from Elfin data in a statistical sense for the in the plane of energy versus L star. This vertical line just marks the empirical plasma pulse location. And the black lines are the contours from this estimate for the electron lifetime. And the yellow curves here marks the modeled electron lifetime based on statistical wave properties and also based on the quasi-linear diffusion model. And from this comparison, we can see that, our quasi-linear field model actually was able to do pretty much a good job in capturing more or less equivalent or good agreement in terms of electron lifetime due to the image wave scattering and also due to the Western mode coarse waves or due to the plasmaspheric haze in different regions of interest as marked here. So that's good, right? So that we can directly validate our quasi-linear field model. Quasi-linear diffusion model actually works well in majority of the time for the long-term electron dynamics. And just to quickly summarize, with this unique data set of pitch angle resolved precipitation spectra, that Elfin was able to actually provide some new insights to different aspects of wave-particle interaction or wave-driven precipitation, to be more specific. So that I will not go into details of each of the items here because we just covered them in the presentation. But because the Elfin is already terminated, right? So what matters more probably is what we can learn from this data set or from this mission. So along this line, I just want to share some of the personal thoughts about what we can do in the next step as a community. So as we already agree probably that we are in the era of this CubeSat or small-sat missions for more targeted investigations in terms of science. So during this kind of time that we can actually conduct more these targeted investigations for different topics. Say that one direct extension from this Elfin mission that we can, first of all, incorporate multiple detectors to reduce the time aliasing effect that we see for those short time scale precipitation patterns, or to even remove the time aliasing from the data set. And equivalently, of course, we can improve on the energy resolution of our detectors, such as in the recent survey CubeSat from LASP. And also we can incorporate simultaneous wave measurements to just review this detailed scattering mechanism that are responsible for each of these precipitation patterns. Or we can even incorporate those simultaneous low energy electron or ion precipitation measurements, so that we can actually improve our existing precipitation models by extending the energy range to aurora electrons or aurora particles to all the way to the relativistic particles in terms of precipitation energy spectra. Yeah. And in the last point here, I just wanted to mention that another thing we can potentially do is to incorporate those in situ atmospheric density measurements to evaluate the detailed contribution of these atmospheric density structures to magnetospheric wave propagation. So with this, I would like to just open the floor for more discussions along this line or about the presentation. And as promised, that I just included all the references on different topics here. Yeah, that's all I wanted to cover. Thank you.
Thank you, Xiaojia. Let's move to Anton's presentation before we have discussion and questions. Anton,
yeah, sure. Just a second. Do you see the screen?
Looks good.
Cool. Okay. Let me move down. Yeah. So as Xiaojia mentioned, I will mostly cover the Elfin results for the Magnetotail region, the night side of your magnetosphere. Some type of precipitations coming from plasma injections or just directly from the plasma sheet. Move. Yeah. So yeah, this is much less nice version of this overview figure which Xiaojia showed us. So yeah, everything above had been covered in the previous one, so I will speak about different type of night side precipitations patterns observed by Elfin, combined in electron and ion data set. Let us first of all establish some baseline for this type of observations. The good story about the Magnetotail, the magnetic field in equatorial plane quite small, curvature radius of magnetic field line quite small, so particles are pretty quickly scattered and form isotropic distributions, and what allow us to make a more or less direct comparison between Elfin measurements and low altitudes and equatorial measurements by different spacecraft missions. That's important for validation of Elfin measurements, but also for our understanding, like where is exactly Elfin is projected along magnetic field lines. So that's one of the example what we can see in Elfin integration with equatorial missions. We deal with the situation when Elfin cross, L shells, of course, it's very wide range of L shells for Elfin. And there are two spacecraft mission near Earth's tail. Themis a little bit closer to the Earth, MMS a little bit further from the Earth. So we have a spectra of electrons from Themis, spectra of electrons from MMS, spectra from ions from MMS. Of course, they covered it's a long time interval, much longer than any Elfin crossing, but fluxes are quite stable in a sense of Magnetotail dynamics, and we generally observe variation, special variation of this fluxes, not temporal one in this particular situation. So how Elfin results are looking like for this night side crossings? We can start non-traditionally from bottom to top. So this is Elfin quasi-trap population of electrons. We're moving from left to right. It's auto-radiation belts, relativistic fluxes. That's what exactly Xiaojia discussed. And this is plasma sheet, like fluxes below 300 kiloelectron volts, quite low level. And there is a transition region between auto-radiation belt and plasma sheet. And if we will plot the precipitating to trap flux ratio, we will see that actually entire plasma sheet is filled by the isotropic fluxes of electrons. These energies are very quickly scattered. We should expect that observation of Elfin in low altitudes are more or less the same as in equatorial fluxes. Then we have this transition region, which is characterized by sort of dispersive feature of electron precipitations called isotropic boundary, and this is Whistler activity in night side. The same story for ions. It's very, very isotropic fluxes of ions in the plasma sheet. I mean, of course, isotropic boundary of ions is much, much more equatorward than electrons. Ions have a larger J radius, have a much larger mass, so no surprise. And if we will just pick up several cuts from, for example, from plasma sheet of electrons, compare them with MMS measurements in plasma sheet, we will see that the fluxes are more or less the same. Spectra are more or less the same, so would give us good hope that what we measure is actually real. If we will go to the transition region, when we can have like more or less relativistic fluxes, and we'll pick up a couple of Themis orbits, which is nearby the yours, between that, like in the moments when we assume that Themis somewhere around the transition region. So we can see that Elfin fluxes is more or less between these two Themis crossings, Themis observations. So again, quite fine. The same story for ions, and this establishes like a background, baseline for our understanding of Elfin measurements. So what we can get from the Elfin, first of all, the good story about low altitude spacecraft that they cross all this bench of magnetic field lines coming from plasma sheet to the to the ionosphere very quickly. So we have almost like a simultaneous snapshot of the entire plasma sheet and inner belt, inner magnetosphere story. So we can just take a look on evolution of the things from orbit to orbit. And this is one of example of such type of observations. We deal with the classical substorm dynamics, the current shed thinning, the equatorial magnetic field BZ is going down, as Themis show us here. Bx is going up in sense of magnitude because of formation of thin current sheets. Then we have a depolarization, some fast plasma flow from the middle tail destroy our thin current sheet. We have a lot of fluctuations of magnetic field, expansion phase of substorm. And we can take a look on the, for example, three Elfin orbits crossing the background. I mean, well before the substorm dynamics, right during the substorm dynamics, and during the expansion phase. So we can check how this, a lower altitude type of measurements are looking like. So this is orbit during the background things. This quasi-trapped electron fluxes, inner belt, plasma sphere, outer radiation belt, plasma sheet, and very smooth transition between the outer radiation belt and plasma sheet, like very nice dispersion of energies with the time, what means actually with magnetic latitude or with the shell. But when we're going to the growth phase, you see how sharp this boundary became. All this bench of the magnetic field lines corresponding to the thin current sheet and New York Magnetotail, they all, come to very, very narrow region in magnetic latitudes. And Elfin orbit just 1 degree, so almost entire New York's plasma sheet is shrinking to the small range of magnetic latitudes. And then we have this expansion phase after depolarization, the entire New York's plasma sheet filled by very energetic particles going up to the, actually up to the MEF energies nearby of the yours. And this is like a classical type of dynamics of magnetic field line reconfiguration during the substorm. Again, comparison with Themis show us that the spectra of Elfin is quite fine. Here, we should more or less trust to what we have in the Elfin data set. There are, of course, not only the Magnetotail type of dynamics responsible for electron precipitation, but different type of transient things, which also can be considered as a part of the substorm dynamics because they are directly related to injections. And I show the three wave type of dynamical precipitations pattern, and one more or less about current sheet scattering, this curvature scattering. So for when we deal with injections in a pre-midnight sector, the hot ions injected into the inner magnetosphere start generating chemical waves, and we observe this nice type of precipitation patterns from Elfin, showing us relativistic electron scattering and precipitating well equator-ward from isotropic boundary, which is somewhere here. I mean, this precipitation patterns generally have some type of dispersion related to the minimum and other resonant energy condition for emic wave scattering of electrons. And this is typical type of example what we observe after in the substorm injections in a pre-midnight sector. In the post-midnight sector, electrons injected to the inner magnetosphere, to the radiation belts, they generate Whistler waves. And these Whistler waves start scattering electrons. The pattern of the scattering is looking like this enhancement of precipitating to Tarab flux ratio, with a maximum and low energies, going up to the few hundred kiloelectron volts, a little bit equator-ward from isotropic boundary, which is maybe not well seen here, but so this type of dispersion pattern. And if we are looking, we were looking on some injection before it's like really penetrate into the inner magnetosphere, a little bit polar-ward from isotropic boundary, we will see that these injections are generally associated with fast plasma flows and wide range of electromagnetic waves. The most intense one is the kinetic Alfvén waves. It's electromagnetic wave emission, generally ultra low frequency one, but due to the very large, very small wavelengths and transverse direction to magnetic fields, these waves can be, significantly Doppler shifted in a reference frame of electrons drifting across the depolarization front, and such type of fine effect provides the electron scattering by kinetic Alfvén waves. This type of precipitation seen in the Elfin as well, and of course in conjugation with STEMIS when we know, so we can check that it's really kinetic Alfvén waves. And the last type of precipitation pattern, which associate with the substorm dynamics, it's this current sheet or curvature scattering precipitation. Sometimes when substorm, this like a really intense substorm dynamics and Magnetotail, the thin current sheet can be formed in the near Earth region and then really propagate almost as close as a plasma pulse. Just one array before the plasma pulse will be stopped, and so we start scattering the radiation belt electrons actually by the curvature effect. That's interesting. I would say mechanism of depletion of radiation belts by just substorm type of dynamics. So like you can see here, this is dispersive isotropic boundary, very sharp one, but still dispersion is there. And this is MEF electron precipitation from curvature scattering, very nice patterns, because sometimes you have fluctuations of magnetic field in the equatorial plane which suppress the precipitation of lower energy part of spectra of energetic electrons, but you still always have this high energy precipitating in a strong diffusion limit. It's very distinguishing feature of curvature scattering precipitations. This is fourth type of example of what we can have in an electron precipitation due to the during the substorm dynamics in the near Earth plasma sheet. Okay, so let us speak a little bit more about this nice transition region between plasma sheet and outer radiation belts. It's really interesting story because in some sense it's just purely Magnetotail type of feature, like formation of thin current sheet. It's mostly associated with ion currents. The electrons have little contribution to this type of story in most of the cases. But somehow these things can influence the dynamics of outer radiation belts, because the thin current sheet propagate closer to the Earth and start scattering Rayleigh radiation belt electrons. Like this is nice example of this isotropic boundary from large statistics collected by Wilkins, and showing us that the current sheet starts scattering electrons starting from 50 kiloelectron volts. This is plasma sheet energy, so like 150 kiloelectron volts. It's a typical energetic part of the electron spectrum in plasma sheet. But then it's going up to the free MEV, definitely outer radiation belt population. So this type of current sheet dynamics and approaching the Earth's magnetosphere can significantly affect the scattering of electrons in the outer radiation belts. In some sense, it's looking like some analog of magnetopower showering when we just remove energetic particle population, relativistic particle population from the higher L shells, but we're doing this on the night side because of Magnetotail dynamics, substorm-related Magnetotail dynamics, which is not so strongly related to the solar wind conditions. This dispersion generally provided by the effect of scattering rate depending on the curvature radius magnetic field lines, and simply speaking on the equatorial magnetic field. So when we have some substructure of this isotropic boundary, we should speak about some substructure of some fluctuations of equatorial magnetic field things. And nice story with this isotropic boundary is actually Elfin measures the isotropic fluxes going up to the pre-MEV or few MEV. So we again can use this feature to check the Elfin fluxes, because before what I have shown, it's just comparison of Elfin flux measurements with the TEMIS. I mean, or with MMS, it's energies about with the upper limit about 500 kiloelectron volts. I mean, to compare with really MEV fluxes, I mean, we need some inner magnetosphere emission. And the good story here is that we really have an inner magnetosphere emission serving during the entire Elfin period. This is ARG rays mission, and rays have a good inclination, allowing the rays to measure particles coming from the plasma sheet. So we can find the events when the arrays and Elfin in the night side sector and compare the spectra of arrays and Elfin when we are sure that the spectra are coming from the transition region from isotropic boundary, where the fluxes should be comparable. And this is one of the examples of such type of comparison with high energy detectors from arrays, and this, like, I mean, outer edge, I mean, of the spectra coming exactly from the plasma sheet. The fluxes are more or less isotropic. The field line is comparable to the transverse. The main part of this outer radiation belt flux, of course, are anisotropic. And the same region has been crossed by Elfin with nice isotropic boundary going to the 2 MeV energy range. So we can plot the ARG spectra here in black, two black lines. I mean, show the boundaries of ARG spectra in the plasma sheet side, and, like, I mean, closer to the outer radiation belt things. And we can plot the all Elfin spectra corresponding to the isotropic boundary between, I mean, just in the same plot. And you see that these red lines are exactly more or less between these two black lines. So what again confirms us that Elfin fluxes are more or less fine, not even for subrelativistic energy, but also for relativistic energy, and provide some additional synergy between the auto radiation belt mission like arrays and Elfin mission in the sense of plasma sheet probing. So what about the substructure of isotropic boundary? Because I mentioned that all this type of fluctuations within the isotropic boundary should be somehow associated with the equatorial magnetic field fluctuations. It's interesting to check how this isotropic boundary is looking like in dynamical type of events when we deal with a non-monotonical structural boundary. And that's nice, two nice examples. Showing us this electron isotropic boundary. We are moving from outer radiation belt, which is here, plasma sheet is here, so this is boundary between them. Anisotropic boundary is much closer to the Earth, much more smooth. But electron, you see, have a lot of substructures, substructure elements, what means that actually we should expect some variations of equatorial magnetic field in this transition region. And the same story for this orbit, just we're going from plasma sheet to the outer radiation belt, see a lot of this substructure inside within the region of curvature scattering precipitations. And if we, again, using the theory, we use some simplified estimation to derive the equatorial magnetic field from this type of fluctuations, we can come to some quite, reasonable type of amplitude of variations. This is one example of this, again, of non-monotonic isotropic boundary things. Ions isotropic boundaries here, we can assume some type of current density distribution in equatorial plane, make us this boundary of electron precipitations, and then recalculated to the equatorial magnetic field, we obtain something like a few nanotesla fluctuations of magnetic field in equatorial plane can provide us this type of non-monotonical boundary structure. And that is happening exactly within the region of isotropization of particles between the plasma sheet and outer radiation belt. But forward from this region, we can see electron precipitation from plasma sheet, which also have sometimes have some non-monotonic type of distribution along the latitudes, what means it's along the L shells. actually. And the most, let's say, the most bright one example is example of this so-called deeps of electron precipitation. That's typical Elfin orbit, again, isotropic boundary of electrons, isotropic boundary of ions, staying a little bit equatorward. And here you see this drops of precipitating electrons fluxes. So really we have a suppression of electron precipitations. Ions are still precipitating. Their curvature radius, their Jerry radius is much larger. They, hardly can be affected by the variations of equatorial magnetic field, significantly affected, so energetic ions. But electrons really can. It's not a big deal for them. So their precipitating patterns can be significantly suppressed, and that's most likely related to the so-called hump of magnetic field forming in the near Earth's plasma sheet. Of course, this is like a sort of speculations, but there are a good type of let's say approach when people use more advanced empirical magnetic field models to reconstruct these patterns of precipitations of electrons and check our assumptions, our understanding of formation of the magnetic field humps and all the substructure for the isotropic boundary. That's like can provide us with both with some sort of verification of empirical reconstructing techniques of magnetic field models, and also advance our understanding of the near Earth plasma sheet dynamics. That's, I think, what I would like to say about electron precipitation from a plasma sheet. But I also plan to mention few type of synergetic synergy between Elfin and other database, which can help us also to recognize some dynamical features and boundaries in a plasma sheet. And one of the very nice type of synergy is when we compare Elfin with the total electron content map, because total electron content provides us two-dimensional structure of like distribution of this things, and we can derive two main type of boundaries from total electron content things, as like plasma poles location and something like inner edge of the plasma sheet. And these two type of boundaries bound the Elfin observations, allowing us better to understand the localization of Elfin precipitation patterns. Another one of synergies, of course, with this fleet of DMSP spacecraft, which provides a lower energy precipitating particles, below 30 keV. And Elfin, when we have a good conjunction between Elfin and DMSP, we get a very nice type of combined spectra of precipitating electrons and precipitating ions, going from the just first tens of eV up to the MEVs, which allowing us to reconstruct the entire precipitating energy spectra of particles, both from plasma sheet, from ring current, from isotropic boundary region. That's sort of important data set for ionosphere magnetosphere coupling studies. And I think the last things which I would like to mention, that again, Elfin can be very nicely conjuncted with the all-sky imagers in the ground-based stations. Previous few case studies show us that sometimes aurora precipitations being conjuncted with measurements in low altitude particle precipitations give us something like some correlation between relativistic electron precipitations and aurora things. And for Elfin, it's very like typical type of story. There is a very large statistics of correlations between Elfin and all-sky imagers data set, showing us that aurora dynamics, like this setting aurora here, well correlate with the precipitation of relativistic fluxes, what give us some understanding of how strong and how effective Whistler waves in precipitating a wide range of electrons, starting from first kevs responsible for aurora and going up to the relativistic energies. That's, I think, what I would like to say in my presentation. I will maybe not read this one, just underline that Elfin provides some type of unique data set for probing of near Earth magnetotail, current sheet, magnetotail, plasma sheet and current sheet, including the dynamics, dynamical features, injection, precipitation from injections, and variations of equatorial magnetic field configurations. And there is a good type of perspective for synergy of Elfin with the different data sets, which will enhance the scientific output from this mission. That's all from me.
Thank you, Anton. Thank you, Xiaojia, for excellent talks. We have a couple of minutes for a couple of quick discussion points or comments. There was already some conversation in the chat. If you have comments or questions, please just unmute yourself and ask.
Thank you for the questions, Robin and Sasha. So I think I put more context into the chat. So feel free to share more of your comments if any.
I have a
yeah.
I'm enjoying your talk, both of you, Xiaojia and Anton. So this is a little bit different from what you talked about, because I know the Elfin has the magnetometers, and also I know it's very difficult. So far, we have not seen any real magnetometer data from CubeSat just because interference, small, shorter boom. Just say, you mentioned about the magnetometers, so can you comment on that flux gate magnetometer measurement?
Yeah, okay, I think I can do just because. We have a data set from magnetometers on Elfin. It's a low time resolution data set. I mean, I think secondary spin resolution data set, providing the good pictures of field line current system. And there are a couple of applications when we use this measurements of Elfin magnetometer to locate the precipitating patterns from Elfin relative to the general field line current system connecting yours ionosphere and magnetosphere. So the data are available. Are available for most of the orbits. For some specific orbits which may not have a good data set for magnetometers, they probably can be restored by request. We still are working to get a high resolution magnetic field data, which will allow us to take a look on the local emic measurements. But speaking about low resolution, I mean spin resolution data, they are available and we use them time to time.
Thanks.
More comments, questions? I think Christine, you put something in the chat. Would you like to?
Sure, yeah. I can just ask real quick. Yeah. Thanks for the presentation. From your last slide, Anton, you had as a possible future work with Elfin and ASIs to determine the upper energy range of electron precipitation associated with aurora. I was just wondering if you could clarify, since obviously Elfin could observe, very high energies from particles that precipitate to altitudes lower than cause aurora, like EEP. So what does it mean by finding the upper energies that contribute to aurora? No,
it was not upper. Sorry, it's my maybe. Oh, it's not my good skills in speaking. I didn't mean, of course, that energies in the Elfin energy range can somehow contribute to aurora. Of course, it's 50 keV to 1 MeV. It's not aurora energy at all. My point was like aurora provide us understanding that there is a low energy precipitations, and if we can resolve them, not only just white light, but also some wavelengths of aurora, we even can guess some lower energy of precipitating particles. And Elfin provides us upper range of precipitating particles. So combination of all sky images and Elfin can give us an entire energy range.
Got it. Okay, thank you.
Indeed, the combination of in situ and the global context provided by ground-based magnetometers is a powerful tool. Thank you. Let's thank both speakers again, and thank you all for dialing in and participating in the seminar. And have a great weekend, and we'll do it again in a few weeks. Thank you.